Hi everyone, I'm Yogadharani, working as Assistant Professor in Department of Computer Science and Engineering at SNS College of Technology. And in this video, I'm going to discuss with you advanced trees like B tree and B plus tree. So session plan is a recap about the previous session, content delivery, activity, and then content delivery and likes. And recap of this session is in previous class we saw about trees like binary tree, binary search tree, and AVL tree and all. And you guys know about binary trees, nothing but what are the nodes are given in a question. You just take it as a first node as a parent node, second node as a left child, and third node as a right child. Likewise, you have to build tree. So binary search tree has no criteria, just build a single parent with at most two childs. Unlike in a binary search tree, parent node has a parent node, and left subtree has the smallest than the parent node, and right subtree has the greater numbers than the parent node. See in the picture here, 54 as a parent node and 21 is lesser than the parent node. So keep it is an left subtree, and left subtree all nodes must be lesser than the parent node. And see in the right side, 72, 60, 84 likewise. So these right subtree must have the greater than the parent node. So here how does binary search perform a large data set stored on a disk? Here, uh, for searching a node or searching a file in a large database, it takes the long time to search particular file. It takes the disk input output, and it needs the uh, performance higher. So in binary, in B tree, searching is efficient because it has the indexing one. So by the end of this session, you guys will be able to explain the structure and properties of B tree and B plus tree. And I give you the differentiate between the B tree and B plus tree, and what are the logics to solve the indexing and database search problems, and visualize the insert, delete and search operations with the real world example. So see here. So I'm going to explain it through the design thinking, and here my pain point of the user is, see here, Ananya, database engineer, see managing a large scale e-commerce platform, and she needs faster data driven with the minimal disk access. So here, how can see design a tree based structure that minimizes disk reads and ensure balanced access time for massive data volume. So in a defined part, uh, she needs to reduce a reduce disk read, and she maintains a balanced automatic through controlled splits and mergers, and also she provide logarithmic of 0 of log n, because in time efficiency and space efficiency, big O of log n, it's mainly for tree purpose only. So search, insert and delete items are ensuring fast, consistent access even for a mass data set. So in this activity part, so this is small activity here. Teams acts as a database block, and each students considered as a node, and stores 2 to 3 keys. It simulates the insert and split operations manually. And we move on to ideate part. Here ideate means binary search tree. It is deep and inefficient. And the other advanced tree like AVL tree or a red black tree, it's good for memory and poor for disk allocation. And B tree and B plus tree optimized for block based storage. See in the example here, parent node has a 3, and main point is that a B tree or B plus tree is it's also called as M order weight tree. Here order means the property behind the B tree is, here order is equal to 3 means, and maximum key must be of m minus 1. So if the order is 3, and it holds the maximum value in a node is 2, that is m minus 1 tree. And what are the minimum child means m by 2. If it is a 3 orders, so 3 by 2 is equal to 1.5, and always we take the ceiling value, so it holds the minimum 2 child. So see here, here the order is 4 might be, so then only it holds the maximum 3 key in a node. So here, see here, 3 data hold there. 13 as a parent node, it's always based on the binary search tree. So 7 has the left side of the parent node, and 23, 31, 43 are the right subtree of the parent node. So from this 7, from 7, 2, 3, 5 are the left subtree, and 7 and 11 are the middle of the right subtree of parent node 7. So in B plus tree, and the main advantage is it takes the copy of the splitting node. See, 7 has the copy of the 1, and then 23 also has the copy of the parent node. So here the leaf nodes, that is 3, 2, 3, 5, 7, 11, 13, 17, 19, 23, 29. This leaf node consists only the data, and it holds the indexing part. The arrows are placed there for every one node to the other node. It marks the indexing for the file search. Next, I move on to the prototype, step-by-step insert process and search process. See, this is the insertion one. If I need to insert one element in this node means, I have to follow the binary search tree operation. So, if any one node is inserted, I must compare it to the parent node, and based on the B tree and B plus tree property, I must place the correct location in the node in the tree. So this diagram shows the block structure and internal leaf nodes here, and main important point is that, and each leaf node contains the indexing to the nearest node. And here technical depth is, here we go deeper the technical core. Yeah, B tree node maps beautifully to a disk block. For a branching factor, it determines how many keys each node can hold. And then implementation can be done in C++, Java or Python in using array or linked list. So all operations like search, insert, delete are run in a big O of log n. So there in every tree, the time complexity and space complexity to be in the operation of big O of log n. It maintains the efficiency no matter how larger the data grows. And then move on to the interdisciplinary and future scope. Here database like SQL, and Oracle uses B-tree uses for B-tree for indexing, and operating systems like NTFS use them for file lookups, and Hadoop uses this B-tree and B plus tree for metadata indexing. And we are not done. Modern DBMS now evolve toward adaptive B-tree and log structure and merge trees, that is LSM trees for high-speed data streaming. And then the summary part of B tree and B plus tree are, B tree and B plus tree is also called as M ordered way tree, and B tree and B plus tree is mainly based on a binary search tree, and it has the properties like, and maximum keys would be in the form of M minus 1 order, and the child key should be minimum child key like M by 2 order. It must obey the binary search tree property. It also mainly used for indexing purpose. And this is the mind map for B tree and B plus tree. And the problem here is for rectifying disk IO and scalability. And B tree, as I told, that it is a multi-way balanced tree. It is mainly for internal data storage, and the efficiency is based on big O of log n. And B plus tree has the data are stored only in the leaf nodes, and linked leaves are in arrange queries, and it's mainly used for database indexing and file systems. And applications who are followed here is database, OS, and search engines. So thank you. I catch you in another video.